Hello, everyone. Hi. Welcome to the Engineering Product and TPM Talks, where we're going to complete our discussion on the databases, it's one of the system design building blocks. I've said that system design problems usually have some similarities. Those specific details are often unique. And in the system design building block series, we're looking at the elements of building blocks that are similar across design problems. This is what I'm referring to as the system design building blocks. One example of a building block is a database, which enables us to store, retrieve, modify, and delete data in connection with different data processing procedures. In this last part, we're going to look at the analysis, partitioning, and analysis of different database types. Who is this for? TPMs, product TPMs, system engineering, program managers, engineering leads, anyone that's really involved in the tech ecosystem. We're trying to complete database. There is a shortage of skilled workers in the United Kingdom. We like to start with a thought of the day, and today's thought is from Tokato Tasso, who says, Fortune rarely accompanies anyone to the door. Fortune rarely accompanies anyone to the door. I think it's spot on, to be honest. As the late great Aliyah said, in case you don't succeed, pick yourself up and try again. If this says something else to you, please like, subscribe, let me know at the bottom. But for me, what it says is that you can't stop. You have to keep on learning to build. You have to keep on learning to design. You have to keep on learning to build your system. Okay, right in the previous, I introduced us to databases, talked about the different challenges, the different types of databases, key stores, etc. And now I want to look at some of the challenges with databases, right? So the first challenge is availability. What happens when there's a fault? If there's a failure on disk, on node, on network, or there's a power outage, what do you do then? As the number of reads and writes and other operations increases, how do you deal with that? And when they're high latency, right, due to multiple entries, multiple records, and time to retrieve those entries, how do you achieve high throughput for your client? Okay, well, for the three I've just mentioned, replication is a solution that helps resolve problems around availability, scalability, and performance on a single node. So what's replication? Well, replication in the simplest sense refers to keeping multiple copies of the data at various nodes, preferably geographically distributed to achieve availability, scalability, and performance, right? Now, just a keyword, it's not one bullet fits all solution. Replication is is relatively simple if the replicated data doesn't require frequent changes. The main problem in replication, the main problem in replication is when we have to maintain changes in the replicated data over time. Other complexities that could arise due to replication are how do we keep multiple copies of data consistent with each other? How do we deal with failed replica nodes? Should we replicate synchronously or asynchronously? So what you see here is you have your user, you have your server, this original database, and you keep copies of that database. Right. So synchronous versus asynchronous replication. There are two ways to disseminate changes to the replica nodes. There's the synchronous replication and there's asynchronous replication. In synchronous replication, the primary node waits for acknowledgement from the secondary node about updating the data, And then after receiving that acknowledgement from all the secondary nodes, the primary node reports success to the client. Now in asynchronous replication is a bit different. What happens here is that the primary node does not wait for acknowledgement from the secondary node, and it only reports success to the client after it has updated itself. So with synchronous, the primary node updates itself, but also updates the secondary nodes and waits for responses from them. But with asynchronous, as soon as it updates itself, it's good to go, right? So this shows you the difference between synchronous and asynchronous. So for synchronous, the primary node writes locally, it writes to the secondary, waits for them to complete, secondary one completes, secondary two completes, then it tells the client that it's completed. But in async, primary node writes, it updates itself locally, it says write complete, while it's still writing to the secondary nodes and waiting for those nodes to complete, right? So the advantage of synchronous replication is that all secondary nodes are completely up to date with the primary node. If one of the secondary node does not acknowledge due to failure or fault in the network, the primary node will be unable to acknowledge the client until it receives a successful acknowledgement from the secondary. So that's one of the challenges. On the other hand, one advantage of the asynchronous replication is that the primary node can continue its work even if all the secondary nodes are down. So you still have some service performance, some service availability. However, if the primary node fails, the writes that went copied to the secondary node, all those writes will be lost. Okay. There are different data replication models. There is the single leader primary replication model. In the primary, secondary, or single leader replication model, data is replicated across multiple nodes with one that's the primary responsible for processing writes to data that's stored on the cluster, as well as the secondary nodes. It also sends writes to all the secondary nodes and keeps them in sync. It's appropriate when our workload is read heavy. To better scale with increasing readers, you can add more followers and distribute the read load across the available followers. However, replicating data to many followers can make a primary bottleneck. That's one of the challenges. Additionally, primary secondary replication is inappropriate when our workload is write heavy. One advantage is that it's read resilient. Uh, there's also multi-leader replication. So in single leader replication, using asynchronous replication, there's a drawback where if there's one primary node, all the writes have to go through it. But multi-leader resolves this because it's an alternative to the single leader replication method. There are multiple primary nodes and they process the writes and send them to all the other primary and secondary nodes to replicate. This type of replication is used in databases with external tools like the Tungsten replicator or for MySQL or MySQL. It is quite useful in those applications where we need to continue to work even if we're offline. For example, think of a calendar application. We can set our meetings even if we don't have access to the internet. Once we're online, it replicates the changes from our local database, our phone, wherever client we use, mobile phone or laptop, to other nodes. Another replication model is peer-to-peer, where um, all nodes have equal weightage and can accept read and write requests. Example, the Cassandra database. It resolves the problem of the primary, secondary node where the primary node is a bottleneck and a single point of failure. It helps to provide write scalability. The peer-to-peer, okay. Okay, now to another key part of your knowledge of databases is data partitioning or sharding. Someone could say, why do we need to partition our data, right? We know data is an asset for every organization. We know that data continues to increase across different organizations across the world. And hopefully we also know that increasing data and concurrent read-write traffic to data puts scalability pressure on traditional databases. So latency and throughput will be affected. Um, and we already said that traditional databases are attractive due to their properties such as range queries. You can query different aspects of the data, secondary indices, transactions with ACID properties. But the fact is that at some point, a single node database is not enough to tackle the load, right? So load, load, load. That's the real reason why we shard. We might need to distribute data over multiple nodes, but still export the nice properties of relational databases. Um, so one solution is to move to a NoSQL-like system. However, the historical code base and its close cohesion with traditional databases make this an expensive problem. So what we can do is we can shard our data. So for instance, data partitioning or sharding, what this does is that it enables us to use multiple nodes where each node manages some part of the whole data, and then the to handle where each node manages some part of all of the data, and then to handle these increasing query rates and data amounts, we strive for balanced partitioning. So it's not just enough to partition your data, you want the partitioning to be balanced. Okay, so what I want to do next is I want to look at different types of sharding, how to split your large data sets into smaller chunks, data stored at different nodes in our network, and how to make sure that sharding is balanced, right? So we have two main types of sharding, vertical and horizontal. Okay. In vertical sharding, we can put different tables in various database instances, which could be running on a physical server. We might break the table into multiple tables so that some columns are in one table while the rest are in the other. It's important to be careful when you're trying to do this, just in case just because the joins between the multiple tables. So when we're trying to shard, we may want to ensure that we will check, depending on design, whether we want to keep specific tables on one shard. Vertical sharding is typically used to increase the speed of data retrieval from a table that consists of columns with white text or binary large objects, which is a blob, BLOB, binary large objects, a blob. In this case, a column with large text or a blob is split into a different table. So if you look at the image here, right, the employee table is divided into two tables. This is an example of vertical partitioning. So the employee table is divided into two tables. Um, a reduced employee table and an employee picture table. The employee picture table has just two columns, right? So employee ID and picture. And the employee table has two columns as well, employee ID and name. The primary key employee ID of the employee table is added in both the partition table and the original table. This makes the data read and write easier, and the reconstruction of the table is done more efficiently. Now, just to be clear, vertical sharding has its intricacies, okay, and it's more amenable to manual partitioning. This is where stakeholders have carefully decided how to partition the data. Now, if you compare this to horizontal sharding, right, horizontal sharding allows automation even under dynamic conditions. So you could say an example of horizontal sharding, right? So sometimes when the tables in the database become too big, and affect read-write latency. You can use horizontal sharding to partition the table or to divide the table into multiple tables by splitting data row-wise. So you have the same columns, but the data is split row-wise. And that's what you see in this figure, right? So this is the complete table here on the left. And then horizontally, you split rows rows 1 and 2 in database shard 1, rows 3 and 4 in database shard 2. Typically, because this can be automated, there are typically two ways this is done, which could be key range based sharding, right? So in the key range based sharding, each partition is assigned a continuous range of keys. An advantage is that it's easy to implement, it's easy to look for specific keys and range queries. Disadvantage is that range queries cannot be performed using keys other than partitioning key. And if those keys are not selected properly, some nodes may have to store more data due to an uneven, due to an uneven distribution of data. There's also the hash-based sharding, which uses a hash function on an attribute. The hash function produces a hash value that is used to perform the partitioning. The main concept here is that to use a hash function on the key to get a hash value and then modify or mod by the number of partitions. Once you found an appropriate hash function for the keys, you may just decide to give it partition a range of hashes rather than a range of keys. Now, any key whose hash occurs inside that range will be kept in that partition. If you look at the illustration here, right? So if you look at the illustration, I'll show you more. I'll show you later. Okay. So now both horizontal and vertical sharding involve adding resources to our computing infrastructure, because sometimes people will ask, what is the best sharding approach? The fact is that both horizontal and vertical sharding involve adding resources to our computing infrastructure. So we scale, therefore business stakeholders need to really weigh in. I don't think it's something that just technology should decide. It's important to have product engineering and business sat at the table to define how you want to scale your resources to prevent downtime, to reduce latency. Now, you can scale resources through a combination of adjustments to the CPU, to physical memory, to hard disk, to network bandwidth. And there are several advantages and disadvantages, right? Depending on how we choose. So for a centralized database, data maintenance, such as updating the data, taking backups of centralized database is easy. You have stronger consistency and ACID transactions than distributed databases. They provide a much simpler programming interface for the end programmers as compared to distributed databases. They are more efficient for businesses that have a small amount of data to store, right? So if you don't have like Amazon retail, then this could be for you. Disadvantages: a centralized database can slow down, can cause high latency for end users. When the number of queries per second increase, then it increases the latency because there are single node limits that we need to be mindful of. And then it is essentially, by definition, a single point of failure. So because of this, its probability of not being accessible is much higher. Availability is low. So what's the advantage of a distributed database? It's fast. It's easy to access data in a distributed data because data is retrieved from the location that's nearest to you, right? Hence, I said we'll talk about content distribution networks later, just so you understand how this works. Uh, Data with different levels of distribution transparency can be stored in separate places. Intensive transactions consisting of queries can be divided into multiple optimized subqueries, which can be processed, which can be processed Some of the disadvantage, I mean, we can process in a parallel fashion. Some of the disadvantages are sometimes you need data from multiple sites, which takes more time than expected. Relations such as joins need to reconstruct complete relations by carefully extracting those or fetching those data. Such operations can become more expensive and complex. It's also difficult to maintain consistency. Is is it's difficult to maintain consistency of data across sites in a distributed database, and it requires extra measures to make this happen in a seamless manner. Updates and backups in a distributed database take time to synchronize. So now what you see is you may have to weigh in on availability over consistency, have eventual consistency. So what about query optimization, right? Well, the data distribution, eh, the database transaction in a distributed database depends on the type of query, the number of sites or shards involved, communication speed, and other factors such as underlying hardware and the type of database used. So both centralized and distributed databases have their pros and cons. We just need to choose them according to the needs of our application. And that brings me to the end of my discussions on database. Just to recap, we looked at replication, we looked at sharding, we looked at the different types of centralized and distributed databases, we looked at different aspects of this and how they impact query latency. Um, Something I'm keen to hear from you is if there's anything else you'd want to see in terms of database. It's a very broad topic, which is why I had to split it in two. I'm happy to have a one-to-one discussion, or if you have any questions, queries with regards to the database, or even just the general knowledge of the technology or any of the building blocks, let me know. Don't forget to like, subscribe. Take care. I will speak to you.